Okay, welcome everyone. Hello. I'm Themis Apsis, Professor of Mechanical and Ocean Engineering and the Director for the Center for Ocean Engineering. I'm very excited to welcome you to the 2024 Robert Wallace Lecture Series of Ocean Engineering. As the President of the American Shipbuilding Company, Robert Bruce Wallace made major contributions to the development of inland waterway shipping. He graduated from MIT in 1898. The Robert Bruce Wallace Lecture Series was created in his honor. The annual lecture series is made possible by a gift from his daughter, Mrs. Chatfield, and her husband, Mr. Chatfield. The 2024 lecture is presented as part of the MECI Symposium 2150, celebrating the history and future of mechanical engineering at MIT. This year, we have the pleasure to have the Wallace Lecture delivered by a distinguished 2OE alumna, Dr. Grace Young. Grace Young is a research engineer and lead scientist at X Alphabet's Moonshot Factory, formerly GoogleX, where her team is creating radical new technologies to protect the ocean while feeding humanity sustainably. She is co-inventor on over 24 patents, and her team's underwater AI was named by Time as one of the best inventions of 2023. An avid sailor, diver, and National Geographic explorer, Grace is passionate about developing tools to better understand, explore, and manage the ocean. She received her PhD as a Marshall Scholar from the University of Oxford, where she was a member of the Engineering Sciences and Zoology departments. Committed to fostering early education about the ocean, she is featured in National Geographic Undersea Lego set and a children's book. In 2019, she filmed the National Geographic documentary Ocean's Breath that explores connections between 300-million-year-old fossils in mountains and modern coral reefs. She has developed robots, imaging systems, and other technologies for CERN, NASA, WHOI, and NOAA. In 2014, she lived underwater for 15 days as a mission scientist on Fabien Cousteau Mission 31, the youngest Aquarius aquanaut at that time. Grace was a 4-year varsity letterman on MIT sailing's team and sailed across the Atlantic for the non-profit Sail Future. Grace also served as a chief scientist for the Pisces 6 deep-sea research submarine and as a liaison to the U.S. National Committee for the UN Decade of Ocean Science for Sustainable Development. Please join me on welcoming and congratulating Grace.
Thank you. Thank you, Thomas. I appreciate it. Thank you. Hi, everyone. It is great to be here. It's really good to be here. Being up here for the Wallace Lecture, it means a lot to me because it's a moment of coming full circle. I dug up this photo from 12 years ago. You recognize? So this was 12 years ago. I was an undergraduate sophomore, and I was dashing between sailing practice and classes. And after this very lecture, Professor Michael Triantafiliou handed me the Wallace Prize. So that year, the lecture was by Professor Milica Stojanovic about acoustics. And the moments after the prize, they were a defining moment for me that very much set me on the trajectory that I've been in the years since graduating. And I'll explain why that was, because just digging up this photo and seeing this photo jogged my memory of something that I'd forgotten. So I remember as the student in this picture, a sophomore at the time, I remember feeling an intense pressure to find my passion as a student. And yet I had just read a comforting piece before the lecture by Cal Newport about how find your passion is misleading advice. It's not necessarily helpful advice sometimes. Really that passion isn't something you follow, but something that will follow you as you put hard work into meaningful problems. And so I decided then that what I would devote my hard work and focus in was the oceans, and specifically building technology for a healthy ocean. And that's why after this lecture and after the prize was such a defining moment for me, and I'm absolutely happy to report that passion did follow. For me, I found that when I go deep and immerse on specific problems, that leads to a sense of passion and fulfillment more than anything else. And I'm sharing that story because I think it might be helpful, it might have been helpful to hear as a student then. Also because I think there's a version of this lecture where I come across as someone who followed their passion and found their passion, when really as a student it might have been helpful to hear more of that context. One of my first independent research projects at MIT was for an environment I knew very well. That was the ballet dance studio. So in high school, I danced with a ballet company, and in high school, I spent just as much time in the dance studio as I did solving math problems and in my school's robotics lab. And I really appreciated how MIT encouraged art and science blending. For me, especially through the MIT Art Scholars Program and the Burchard Scholars Program. And this was my project for 2671 with Barbara Huey, Measurement and Instrumentation. And I'm seeing nods, yep, this class is still on. And I worked on the Connect code with Professor Ramesh Raskar's class, Computational Photography, and with his group in the Media Lab. And I was measuring with a Microsoft Kinect sensor differences in a dancer's alignment during a pirouette turn. So the pirouette is this fundamental turn, and the difference between landing 8 spins versus 1 spin comes down to micro changes in a dancer's alignment. So her head has to be perfectly aligned with her torso and her knee and her toe in order to complete so many spins. But as the person spinning, it's hard to know which points of your alignment might be off. And so this early computer vision system, it helped pinpoint which elements of alignment might be off for a dancer and then help her train more effectively and with less wear and tear on the body. So this project at MIT, it was a stepping stone for me to work on other advanced camera systems, but for another difficult environment. Yeah, when I say that I'm an ocean engineer, that I build technology for the ocean, a surprising number of people, maybe not people in this room necessarily, but a surprising number of people respond telling me, oh, that sounds very specific. That sounds very niche. And to that I say, look at our planet. The ocean is not niche. Yeah. It's essential for life on Earth. It regulates our climate in a unique way, and it's a really challenging place to work. I mean, it's saltwater. Saltwater kills electronics. If I spilled my water on the setup right here, we wouldn't have the slides. It's pitch black in most places. It's cold. GPS and Wi-Fi don't work underwater, and our human biology limits us. I think one of the reasons why we know relatively little about the ocean is because our human biology limits us. So this photo, for example, it shows all of the gear that I needed to spend just 10 minutes at 330 feet deep. And 330 feet deep, it's deeper than most scuba divers can go, and it took years of training and all of this gear, 6 tanks I'm wearing, and yet that is barely scratching the surface of the ocean, okay? The average depth is 12,000 feet. And so we obviously unquestionably need technology, breakthrough technology to explore the ocean. We need robots, we need AI, we need all of the tools in our toolbox to better understand the ocean. And yet I'm calling this talk, Don't Let Robots Have All the Fun. And by that, I'm saying that because I'm about to share stories that I wouldn't have if I had sent a robot in my place. And I sometimes need a reminder to get out of the lab. Maybe we all do. I've also found that putting yourself out there and getting as face-to-face as you can with a problem can be hugely clarifying and motivating in developing solutions, and it can help you be confident that you're developing solutions for the right problems. And I feel that's key for having the biggest impact, especially when we're working on big existential problems like climate change and ocean health and how to sustainably feed our planet. I've had the chance to experience the ocean in a way that's different from most people. I became an aquanaut when I lived underwater for 15 days on a research mission led by Fabien Cousteau. Fabien Cousteau is the grandson of famed ocean explorer Jacques Cousteau. And 6 of us aquanauts lived in this underwater habitat on the seafloor, 20 meters deep off the coast of the Florida Keys. A lot of people mistakenly call the habitat a submarine, but it's different for some important reasons. So for one, the habitat is bolted to the seafloor. And 2, more excitingly, inside a submarine is at 1 atmosphere of pressure, the pressure we're all breathing now, but inside the habitat was kept at the same pressure as the surrounding water, so about 3 atmospheres in our case. And that meant that we could enter and exit the habitat as we pleased, and we spent 8 to 12 hours every day out in the water diving, conducting research. We were doing half a dozen different research experiments in collaboration with Northeastern Marine Science Center. We collected DNA samples on sponges. We looked at communities of plankton and how their composition changed during the course of the day. We led daily Skype in the classroom sessions with students all over the world. And spending 8 to 12 hours a day in the water was special because on regular scuba, at this depth, you could only spend about 45 minutes per dive and do maximum 3 dives a day. And so having all that extra time in the water meant that we could do research that we couldn't do on regular scuba. And I did have to miss my graduation ceremony for this mission, but I kept up tradition and flipped my brass rat underwater. I felt being underwater for those days, I started to feel like a true marine mammal. So in this photo, in the sun shadow to the left, you can see the outline of these eagle rays. And here's the same eagle rays this is swimming outside the viewport in our bunk room. And to this day, they're my favorite animal. Just looking at a picture of them makes me smile. And now, I was there because I helped adapt an ultra high-speed camera to the underwater environment. So our eyes, we see it around 30 frames per second, and the slow motion setting on an iPhone films at 240 frames a second. This camera could film at up to 18,000 frames per second. And that meant that we could see things that moved really fast. We could see them in slow motion and underwater. And the camera itself it was developed by an MIT alum named Mike Matter, who lives just around the corner from me in California right now. And he named it the Edgertronic, of course, after a famed MIT professor, Doc Edgerton. And what's cool about that is that it was a moment of coming full circle again, because Doc Edgerton worked with Fabian's grandfather, Jacques Cousteau, back in the day on some of the first underwater cameras in slow motion photography. And I wonder if they could have imagined how 50 years later, people would be using derivatives of their technology in a new way. This is a photo of me and fellow aquanaut Liz operating the camera. And I am upside down, but believe it or not, I was very comfortable in that position. So these helmets that we were diving in were really heavy underwater. They're designed for big Navy divers. And the helmet underwater was 20 pounds negative. And so we were diving for so many hours of the day. Every couple hours, I would let myself take a break. And taking a break, my head would do the natural thing was that it would fall to the seafloor. And then my legs would float up with the neoprene. And I was taking my break, and that's how I found myself looking at a fairly bland patch of sand for about a full minute before I realized that I was staring eye to eye with a very well camouflaged mantis shrimp. So this mantis shrimp is about the diameter of a quarter. And as you can see, it's well camouflaged in the sand. And these creatures are especially interesting because they move really, really fast. So real time, looking at this mantis shrimp, I could see a couple flicks of sand here and there, but I didn't see anything particularly interesting. I didn't see it moving. Only with the ultra slow motion camera did we see this. Yeah. Yeah, the mantis is leaping out of its den to grab that goby and staring at this in real time. I had no idea that this happened, that the goby had swam by. I just saw a flick of sand because this happened faster than a bullet comes out of a gun. It was only with that high-speed camera, only with the technology that we could see what was happening right in front of us. And we think this is the first time that the mantis shrimp was filmed in high speed in its natural environment in the wild. To get a sense of how slow it is to, sorry. You could just see how slow those pieces of sand were moving. Now, another day, I was walking on the seafloor, collecting data for other graduate students, and in the distance, I saw a poof of sand, and then a couple feet away, I'd see another poof of sand, a couple feet away, another poof of sand, and it looked like a ghost was walking on the seafloor far away. And only with the camera could I filmed it and could I see what was really happening, and here's what we saw. It's a lizardfish, and it makes two S shapes to bury its body in the sand and stay camouflaged, and then super fast, it comes out of its hiding space in the sand to move on to its next location. That was really happening. And again, seeing it in real time, I had no idea that this was even a fish. Only with the technology could we see what was really happening right in front of us. Things don't always happen as you expect them in science. So we had originally brought down the camera to explore an unproven hypothesis about the Goliath grouper. The Goliath grouper is this massive 200-pound fish, and divers had reported feeling a boom in their chest, like that, when the Goliath would feed near them. They would have feel the boom, and then they observed fish looking dazed in front of the fish, and then the Goliath would come and swoop up its feed. So the hypothesis is that maybe the Goliath is on purpose creating a cavitation bubble in its mouth that forms and collapses in an instant and creates that boom that divers were feeling. Now, to investigate that, we thought, we could use, you see where I'm going, the bubble forms and collapses in an instant, faster than the human eye could see, so maybe we could use the ultra high-speed camera to film that bubble happening. And it took us several days of being around this Goliath grouper for it to get comfortable enough in our presence, and it did boom right in front of us. This photo, it boomed right in front of my fellow aquanaut, Liz, and yet we didn't have the camera set up, and we realized we would have had to have the camera inside the fish's mouth to see it, so we didn't get to prove that hypothesis. But it just goes to show things don't always go as you plan in science, and yet when you're working to solve a problem, sometimes what you're working on has unexpected outcomes and applications in other areas. Yeah, and I think too, it's another reminder for me that getting out there and getting face to face with a problem as close as you can is important for developing solutions. And things came full circle for me again when I got to dance ballet on top of the emergency air supply cylinders outside our habitat. Yeah. And getting to be an aquanaut is a rare experience, but now kids can pretend play with an undersea lab Lego set that I helped pull together in collaboration with National Geographic. I hope that when these kids grow up that they will build more underwater bases so that perhaps living underwater will become less of a rare experience. Fully immersing cemented my motivation to keep working on technologies and solutions to help us better understand and manage the ocean. And it attracted future generations to the ocean as well. On Mission 31, we surpassed our goal of reaching 31 million people with a message about the ocean. I especially love stories. I still get stories from students and their teachers. I've seen Halloween costumes of ballet, dancing, scuba diving robot builders, for example. And one kindergarten teacher sent me the drawings that her students had done, her kindergartners have done after engaging with some of our lecture material. And most of the drawings, all of the drawings were of cute ocean animals, of fish and rays and the habitat. And one of them was completely colored black crayon, like he must have used the whole crayon. And I asked the teacher, I said, hey, what's up with that one? And she said, oh, that's because you said it's really hard to see underwater sometimes. Sometimes it's pitch black. And I thought, that's a really cool way of thinking about the problem. So after Mission 31, after MIT, I continued digging into ocean research at Oxford on a Marshall Scholarship for my PhD. And I must say, Kim Bernard, sorry to embarrass you if you're in the room, I don't know. But she and the Global Education Office at MIT, they played a huge role in my journey post-graduation. So that is another element of MIT that I am hugely grateful for, Kim and the Global Education Office. I still, to this day, 10 years later, I repeat Kim's words when I help students prepare for school or job interviews. Also, Oxford made me really appreciate the infinite corridor, because at Oxford, I had to bike across the city to go from the engineering department to the zoology department where my marine collaborators were. It just made me really appreciate how the infinite does foster interdisciplinary connections. So in my PhD, I dug into a concept that I'd observed in Aquarius, which was that well, the outside of the habitat is this incredible living reef. They made it the Bing homepage while we were there, and it's been a marine protected area for over 30 years, so it's teeming with different kinds of life. And being there, I couldn't help but compare the living reef to a city like Boston, with different life forms frequenting different structures underwater, with different patterns in day to night, and with different creatures frequenting different areas and different structures on the reef. I like to call coral reefs the megacities of the ocean because they host an estimated 25% of marine species, and yet they cover less than 1% of the seafloor. And we know one reason why they're able to do that is because they have this gorgeous, mathematically complex 3D geometry. So it's been shown for decades that the more complex a 3D structure is, the more fish and other species it tends to host. And the reason for that is because the more complex a 3D structure is, the more surface area there is for fish and for food and to grow on, and also the more nooks and crannies there are for species to hide on the reef. But how do we measure structural complexity? That's a question that I dug into for my PhD research. And understanding the 3D structure of reefs, it's important because it helps us better appreciate natural coral reefs, and it can help us build better artificial reefs. So when I started my PhD, one of the most popular ways, or the most popular way to measure reef structural complexity was called rugosity. And to do that, researchers placed a chain over the reef, and the island where I worked, it was literally a toilet bowl chain, because that's just what the one hardware store on the island had. And so what they do is they drape the chain on the reef, and rugosity is the ratio of the draped length to the full stretched out length of the chain. And even that coarse measurement correlates significantly with species richness. And yet it's obviously not ideal. It can be damage to the reef. So wouldn't it be great if we could 3D model the reefs instead? Now this is a 3D model done by my friends at the Hydros Foundation a little bit after my PhD. And it shows that gorgeous 3D structural complexity of the reef. But now to get this gorgeous 3D model, they had to wait weeks for the water to be ultra clear in the waters off Hawaii. And they used a DSLR camera with custom lighting. And they used a dedicated desktop rendering for many hours. And that kind of process just wasn't practical on some research schedules too. So here's my intrepid team of 4 master's students that I worked with. They wanted to go diving every day to study the reef. We worked on an island called Utila off the coast of Honduras. And we had to make do with the resources that we had available to us. And so nearly every diver on the island had a GoPro camera or a NoPro camera and had a laptop, sometimes a laptop 5 years old. And that's what we had available to us to try to make 3D models of the reefs. And when we first made the models, they looked like this. They were obviously wrong, and it did not work at first. But after iterating on the methodology and improving the software, we were able to get usable 3D models of the reef. So my goal here wasn't stunningly gorgeous 3D models like the model you saw before. It was models that were usable for 3D structural complexity analysis on a reef. So this isn't color corrected, for example. And you needed something that could be done on an island from a student's laptop with the cameras on hand and in realistic water conditions. And we were able to recreate traditional rugosity measurements with meaningful precision and accuracy. We could also generate other metrics of structural complexity that aren't possible without a 3D model. So for example, we measured fractal dimension, which looks more at the nooks and crannies of a structure. And that would be really hard to quantify without a 3D model. And then having the 3D models, it enabled us to feed them into a machine learning algorithm that could, for example, guess whether or not a surface would have a high or low fish count, for example. So at this point, I turned the 3D models for this model into a topographic map. And you can see the left half of the images, those had a low fish abundance, the right half had high fish abundance, and the machine learning model could start to guess the difference between these two. I found that machine learning is especially powerful when the patterns that we're looking at are subtle. Subtle to the human eye. I find that that's where computer vision can be especially helpful. It was because of my 3D modeling and mapping work that NASA called. I ended up working for NASA for a summer during my PhD to 3D model asteroids in space. That might seem unrelated, but the underlying technology was similar, making 3D models from low quality images. And in this case, the low quality images were the radar images, and NASA needed to 3D map near Earth object trajectories to measure how close they would come to Earth. And so they paired 12 of us AI experts from around the world. They paired us with planetary scientists to work on this and other problems. Don't let robots have all the fun. For me, it's a reminder that solving a real problem, like making 3D maps from low quality images, can have knock-on applications in other spheres, for example, asteroid modeling. And also at NASA, they told us that your chances of getting killed by an asteroid are greater than your chances of getting killed by a shark. So today I work at a unique place called X, the Moonshot Factory, not to be confused with the former Twitter. We used to be called GoogleX, and our mission is to invent and launch breakthrough technologies to solve some of the world's toughest problems. We look for solutions that might take 10 years to create, but if they succeeded, would have at least a 10x impact on real world problems. And we call ourselves a factory because we're trying to repeatedly produce world-changing innovations. So some of the companies you may have heard of coming out of X are Waymo, self-driving cars, and Wing, which does autonomous delivery drones, and Brain, which has done foundational AI work. And there's been a ton of others too. There's a geothermal energy storage company called Dandelion, and healthcare innovations through Verily. My team, called Tidal, is X's moonshot for the ocean. And our mission is to protect and restore ocean health while still sustainably feeding humanity. And we've developed breakthrough technology that some people said wasn't possible, and 5 years later, we've commercialized it around the world. So at Tidal, we believe that sustainable aquaculture is one of several necessary solutions to support our planet's growing population. And I think there's three important things to understand there. One is that today, over 3 billion people rely upon seafood as a primary source of protein. And already, more than half of that comes from the aquaculture industry. And fish are a much less carbon-intensive source of protein compared to other sources of animal protein. And yet, the aquaculture industry faces plenty of rightful criticism, but there are ways to grow fish in a way that has minimal impact on the environment, and at Tidal, we want those ways to be the default. I'm gonna use the word pen a lot, fish pen, and this is what I mean. So this is a photo of one of the aquaculture sites that we work in, and each circle is a pen. The circles could be like twice the diameter of this room, so they're quite large, and underneath is a net that's housing the fish. Today, a challenge is that fish farmers don't have a lot of visibility on the fish that they're raising, and that's just because the fish are underwater. They're in a dark, poorly lit environment. And so what farms do now is they'll manually sample 20 fish out of a pen that will house 250,000 fish. And with a sample size that small, it's hard to pick up on trends and you can miss things. And that's where technology can come in to help. So let me tell you about the technology we're developing at Tidal. This diagram shows the camera and sensor suite that we've developed. The camera and sensor suite, it's in the middle. The 2 circles represent our stereo camera system. This diagram is misleading though, because it is not to scale. The pens are actually so huge that it is hard to find the fish sometimes in the pen. Also, this potentially makes it look like the pens are static and rigid, but one of the challenges is that these pens are on the ocean, and so that circle, it's flexing and moving, and the net is swaying and moving. And that's a really challenging problem. I was talking to Wim today about modeling non-rigid structures underwater. Makes it a difficult place to work, and we absolutely can't risk the camera rubbing against the net because no one wants to affect the integrity of the net. So it's a hard and challenging place to work. For scale though, so the camera that you saw in the picture, for scale, it's next to me in this photo. This is our team. The camera is under the arm of my colleague right there. And here's an example of a typical scene in a fish pen. You can tell it's chaotic, it's dizzying, there's a lot going on, and it's also kind of beautiful, I think. I'm someone who loves spending time underwater, and yet even if I could have my head here 24/7, I would miss things. There's too much going on, the patterns are so subtle. And so that's where the computer vision and sensing systems that we've worked on have come in to help. So in this video, what we're doing is we're tracking each fish and whether or not it's eating the pellets that are falling down, and the pellets we're also tracking. And that's important because it lets farmers know whether or not fish are eating the feed, and that saves cost because they're using just the right amount of feed, and it also reduces waste so that pellets aren't falling to the bottom of the pen uneaten. While doing that, we are also precisely measuring the weight of each fish, and we're looking for any signs of sickness on each fish. And we're counting a parasite on these fish. The parasite is about the size of a sesame seed, and it's camouflaged on the fish. We're counting those numbers. And that's important because it lets farmers know whether or not the fish are growing as expected, and it lets them catch any health issues as soon as possible so that they can make an intervention. So the farms we work with, they don't have to use any antibiotics. And our tools let farmers, regulators, and companies make data-driven decisions about how to care for the fish. And for example, our tools and data can let farmers innovate and trial on new different types of fish feed. So it used to be that fish feed was 70% wild-caught fish, exacerbating the problem of overfishing. Now they've gotten it down to 25% wild-caught fish in the meal, and there's innovative ways to get it down to 0% feed. For example, using algae that grows omega-3s. But now farmers can trial new feeds, and they can tell whether or not the fish are actually eating the pellets, whether or not they're growing as expected without any adverse outcomes. So technology is helping farms switch to more innovative kinds of feed. And we were, in 2023, we were named one of the best inventions of the year, our underwater AI. People had this idea for a while of using cameras in the fish pens to sense what was going on, but no one had made it work. Like when we applied off-the-shelf technology to the footage we were looking at, for example, it was saying that the fish, some of them were umbrellas, for example. And it took us almost 5 years of refining the perception of collecting data and working hand in hand with feedback from real ocean farmers to get it working in a meaningful way at scale. I find especially that when we're developing AI, it is easier than ever to get stuck in a lab, to get stuck behind a computer screen, and sometimes it's not even clear what it means to get in the field. But for my team, getting face-to-face with our users was hugely clarifying in making sure that we're solving a valuable problem, and that was important to do before jumping in and building the AI. So these photos, these are from my team. We spent several weeks immersed with the teams running the fish farms to understand how they would interact with technology and how they could use tools that we would build them. And I think this is key, again, to have maximum impact. In preparing for this lecture, I got to read the 8th Wallace lecture by Dean Gerald Wilson, he was the Dean of Engineering in 1988. And in his Wallace lecture, he expressed a fear that MIT engineers were becoming too isolated, too compartmentalized, too myopic. And yet he saw that the world needed exactly the opposite. It needed engineers that could be synthesizers and that could lead multidisciplinary teams to solve real problems. I think he would have been proud of the MIT that I experienced 3 decades after his talk. And I think, especially as we're dealing with big, daunting existential problems like climate change and ocean health, it's easy to lose passion or motivation because the problem seems so vast. Also, people often hope for a magic bullet technology to come in and fix the problem, when really I'm comforted knowing that it's going to be a multitude of different solutions coming at the problem from different angles to come at a solution. And I find those problems are exactly the kinds of problems that engineers are perfectly suited to solve. So let's keep getting out there and keep exploring and not let robots have all the fun. Thanks again for bringing me back here.
Thank you very much. And questions?
This is all really fascinating, but just a nerdy diving question. If you've been living at 3 atmospheres for that long, what's the decompression process?
Oh, good question. We had to decompress for 18 hours to return to the surface, and it wasn't too bad. People ask me all the time, what did that feel like? And honestly, I slept for almost the whole 18 hours. I was so exhausted by the end of it. We wore oxygen masks to accelerate the process. And a lot of the training that we had to go through to prepare to saturate was actually to make sure that our instinct, should anything go wrong, that our instinct wasn't to go to the surface, because then we'd get decompression sickness. Instead, they wanted our instinct to be to go back to the habitat so we could go through the proper 18 hours of decompression.
Did you decompress in the habitat?
Yes. Yeah, we decompressed in the habitat, so that's why I could fall asleep. Slept, and they slowly raised the pressure in the habitat, or lowered the pressure down from 3 to 1 atmosphere. Yeah.
Where were the pens?
Where were the pens? The fish pens we work with are all in Norway right now in the fjords. Yeah, and we're in a couple hundred pens like up and down the coast of Norway. Yeah, in the blue shirt.
The biggest piece of ocean news that I've been reading about lately, and I don't appreciate the state of our knowledge, is the whole issue of ocean heating and how much thermal energy is now in the ocean as compared to what it was, and how effectively and in what manner is the ocean acting as a heat sink, which of course is finite and can't last forever. So could you give us some insight into what's going on?
Yes, so engineers have joked sometimes that the ocean is our greatest heat sink. I know Microsoft was experimenting with putting some data centers underwater to take advantage of the heat sink properties. Unfortunately, putting any electronics underwater is really hard, as I mentioned. And I'm not sure I know what to say. And I'm remembering the statistics. The ocean has bared the brunt of climate change and absorbed more human-emitted CO2 emissions than any source on Earth. I just know that the problem is getting worse and worse in terms of acidification and warming on the ocean, and it's had big effects on ecosystems underwater, and it's had big effects on our climate and so on human life too. I think that's maybe the extent of my knowledge on there, and it's something I'd like to keep studying and invest in more research too. Yeah, I don't know if anyone in the audience is working on that or researching that, I'd love to hear.
On the topic of don't let robots have all the fun, a lot of your work has AI in it. And is the advent of large language models, as it relates to the kind of work you do, going to change things?
Yeah, I think so. I think the foundational models, large language models, are changing the field of AI, and so like we keep updating our computer vision models, and so those kind of models are state of the art. I was just talking to a professor about which kinds of models might make sense. For now, it's like, I mean, like many people, I use ChatGPT a lot and Google's Gemini to like edit text, to come up with ideas. I think we're still seeing how it's changing the field. I will say in aquaculture, though, something I've realized is that it took us about, I'll just tell you the story. It took us about 1 year to get to what I would call a promising prototype of the technology that I just talked about in the slides. And after 1 year, though, the last 5 years have been about going from the promising prototype and demo stage towards going into a technology or real product that farmers could use and rely upon every day, making that demo reliable every day in the ocean in different conditions has been a challenge. And so hardening technology will be a challenge too in big industries like that, where you really can't risk fish escapes or a negative outcome. That'll be challenging as we're testing new equipment. Another challenge we have in terms of the large language models is that our farms are still offline. A lot of them are. It's hard to transmit that many images like up to the cloud from there. And so we need models that are running on the edge usually. And so we want smaller models to run sometimes. So that's another challenge. Yeah, so those are some of the things that I'm thinking about. Yeah. Yeah.
I was talking to an undergraduate student who was starting. Sorry. I was talking to an undergraduate student who was starting recently. He didn't know how to start solving problems. Okay. So my question for you, please, is what, for the many diverse problems that you've been involved in successfully, do you have a first or second step that usually gets you started and into the problem?
Into the problem. Oh, that's a good question. I found for me, like I said, like immersing in the problem has been huge, and sometimes that takes getting out of my comfort zone. So like as a software engineer working on our computer vision, of going out and spending weeks living at a fish farm on a remote town in Norway, but spending each of those days working with the farmers, I found led to natural solutions, because they are running these operations day to day, and we're coming at it from a technology mindset. It starts to become clear which types of solutions would work in practice. So I find that very clarifying and motivating in working on the next steps of the problem after the problem's identified. And if you don't already know a problem, like just getting out of your comfort zone again and spending time in the field. I got to chat with some undergrads today who in the summers they're going to the Azores. There's an ocean engineering program there, and they're collecting data. They were developing drifters, and they all like just had great stories and were really enthusiastic about the work that they were doing there. So I think getting out in the field could be really clarifying. Yeah.
So now, talking about robots, you didn't show any.
Yeah. So
could you talk a little about what you guys are looking as big challenges on that space?
Yeah, big challenges in what are you thinking? Like climate change, like ocean health, like big, yeah. Yeah. Oh, how it's challenging. Yeah. One challenge is like I shared, like the off-the-shelf models we tried for the types of footage I was looking at. They were detecting the fish as umbrellas. Like the footage is just different enough from what was trained on a lot of models to not quite work. And so one challenge we had was collecting enough data from this specialized underwater environment to fine-tune those models to get them to produce meaningful results. And that took a lot of time with the farmers, patiently collecting data. Now we're processing a couple million images every day of this footage. And another challenge was having processes work offline and in real time. And that was especially important for the fish feeding operations, because you can't risk having feed like stop or not work if we don't have internet connectivity. And so getting some of these large models to work offline and reliably was a challenge. It was also a challenge to make sure that the tools we were building were something that farms could actually use and that they could trust. And for that, we needed, I think, just a lot of data and a lot of times where our technology experienced different conditions, like big storms underwater or unusual events underwater, to show robustness over that. So that was a challenge. With the 3D modeling, the challenge was getting it to work at the time with the low quality, like shaky footage underwater. Those are some. With the camera, with the high-speed camera, it was that we were dealing with low light environment. So that high-speed camera, since the shutter is only open for such a short amount of time, there's not a lot of chance for light to get in the camera. And underwater, we don't have a lot of light, and so though that was a challenge. So we did lower resolution images to get the video that you saw there.
Yeah, I'm curious, in the fish pens, are there any like transport-related problems, like temperature gradients, pH? Are there other things being measured that, because I imagine like the fish are swimming around and so there's some mixing, but you know, food is coming in, their waste is coming out, it's accumulating. Like, are there things that could be optimized there in terms of getting the right density of fish and knowing when to harvest and stuff like that?
Yeah, well, we do measure temperature, and I think a valuable sensor, one of the most valuable ones, is the dissolved oxygen sensor, which is related to temperature, and that is important because we want the fish to live in plenty rich oxygenated water, and if the oxygen levels ever go low, then the farms need to bring in an oxygenator to bubble up the water. In Norway, we're in a bit of a unique place because the fjords where the pens are, they're deep. So right off the coast, it goes to almost 100 meters deep. And they're right against the Atlantic Ocean, and so you have the force of that water, like completely recycling the water basically in the fjords almost twice a day. And so we don't see local temperature gradients too much in the size of the pen, even though that pen is huge. It's small on the scale of the fjord and the ocean. And we tend to see plenty of fresh water, and I haven't heard of our farms needing to bring in an oxygenator, but that's one of the sensors that's been really important. I think there's more work to do too. I know like the parasite, for example, its life cycle is very dependent on temperature of the water. And so if we could figure out a way to integrate the temperature sensing with that parasite detection or prediction, it could be really powerful. Yeah, there's probably more work to do there. Yeah, Jason?
What is the status of the continuity for individual fish of learning about their health progression over time?
Yeah, of individual fish. So I was just talking to, I think that was today, about like you can detect individual fish. They have unique spot patterns on their face. So you can kind of detect who's different, like the different fish individuals. And we've had some projects in that, and we haven't needed to push it too much further in the end, but I think it's a really, really neat problem, an academic problem. What we found is needed is to track the wellness of fish overall. So even if there's just like 10 individuals out of a pen with 250,000 that might have a condition, like a wound on them, then we can let the farmer know so that they can bring in a fish veterinarian or inspect what's going on. And if there's really a problem in a pen, the numbers are reported to the regulators in Norway so that they can act and help those farms. Yeah. I saw there's a cool video online about someone has a really clear vision for personalized fish welfare and medicine, and I would love a future with that. I think there's still work to do, but it would be cool. Yeah.
Good afternoon. Thank you. Can you tell me your perspective on where commercial considerations come into Google's filter of the big problems in the world to work on and solve? Yeah. Where commercial filters come in for the problems that Google works on. That's a challenging problem, and it is probably above my pay grade, I will say. Google's, but why I started there 6 years ago, I mean, Google wants to make a dent in the big problems facing our world, and how to sustainably feed the growing population is one of those massive challenges. And that's why us working in the aquaculture space towards that problem, why it's fit with X's mission to solve big problems. And it's that unique sweet spot where we think technology can actually help the problem. There's a lot of
big problems out there that I don't actually think technology like has a space to solve, and technology might even just make it worse. And so this we found was a niche spot where we needed breakthrough technology. The technology would actually help the problem, and it's a huge problem. So maybe that helps answer. Yeah. Yeah.
Thank you for the great talk. I'd like to follow the previous question. If you have any suggestions on how students can get exposure to such interdisciplinary niche problems. For example, how did you get started working on the current problem which you explained?
Yeah, that I'm working on now.
Yeah, and I have the second question too, sorry. How do you validate the data that you got out of the fish cultures in such complex environments?
Yeah,
Thank you.
Okay, first question, how students get involved in interdisciplinary projects. I found at MIT, I'm so thankful for the research that I got to do with professors working on the UROPS programs. And then every summer working on an internship. So worked at Woods Hole for 2 summers with Hanu, who's here, hey. And those were incredible experiences to expose me to different disciplines and taking classes in different fields while I could. You know, I regret not taking, I took so many classes, but I regret not taking this one class, which was called air conditioning. I don't know if it still exists. It was in architecture, and I thought, just reading it, I thought, what that would be so interesting to have on my transcript, air conditioning. And I just regret not taking it because, gosh, air conditioning systems are everywhere, and it actually is so complicated, and it is contributing to the problem of climate change. And so, but just like, when else am I now never have the opportunity to take a class on air conditioning, I'm afraid. And I wish I did. So taking that opportunity to try different things and talk to different students and do UROPS and do like a research project for 6 months. I actually miss that now in industry. Right now I can't really just leave for 6 months and do something else. I wish I could, but that really worked for me. And then your second question was, sorry, what was your second question?
Validating the data that you got out of.
Oh, validating the data from the fish farms. That was a huge part of our work, and honestly took more time. It took way more time than developing the actual technology, I will say. So, and like I said, right now the state of the art is these 20 fish manual counts, and like I shared, that's just not enough to really precisely validate our system. We thought our counts from the cameras were more precise than the 20 fish counts, and we do get numbers that are different sometimes than those 20 fish counts. And it's still an ongoing discussion because I'll have some people say like, oh, but your number is different from this 20 fish count, and we have to explain like what's statistical significance. And oh my gosh, I had to have a meeting with the Norwegian government, and I walk into the meeting with my plots and my graphs and my confidence intervals, and then I remember the government administrator, she just starts with, she's like, hey, I don't like math. And I thought, oh, okay. So just a lot of like discussions and like graphs that don't look too graphy. That was a big part of our work. We worked, and again, working hand in hand with farmers. So they want this technology to be more accurate, and we worked with them. We did samples of 1,000 fish to ground truth our vision systems, for example. Yeah. Yeah, John, hi.
One more last question. Thank you,
Okay.
Grace.
Oh, we're almost at time.
You are the perfect embodiment of go forth and measure.
Oh, good.
And hopefully the uncertainty analysis from 2671 was helpful.
Yes,
yeah, and,
absolutely.
But if you, what about getting beyond the fjords and into the open ocean? Like imagine doing this at scale and dealing with storms and like could you imagine like continuously sort of deployed far offshore aquaculture systems? Could that happen with robotic technology?
Yeah, absolutely. I think there's a strong case for that. I think businesses want that to happen. So the idea is to move farms further offshore because that way you have even more water circulation and flow, and disease could be less of an issue, and you're less space and resource constrained. The challenge is it's just hard. Like working in the ocean, it's hard. And so whenever you need something maintained or checked or a net cleaned, you'd have to send people out to that remote place, and that gets expensive, or you have to have robots monitoring it all. And we're all working on technology and robots here, and I think it's something that we have a pretty clear like product vision for, but that we're not quite there yet with the technology. Like even what we're working on at GoogleX. So some of our cameras, I think they could work in a future aquaculture pen like that, but we're not ready yet with the tech. Yeah.
Is anybody trying to relate your results to bulk measurements in the pen? Like sound transmission, light transmission, turbulence level, which you can relate to the number of fish, but anyone trying that?
With you said with light measurements to connect to the
transmission, for example.
Yeah.
Sound transmission.
Sound transmission. We would like to do more of that. I don't think we're doing what you said necessarily. So sound does play a role in the pens. They know when if there's a predator, like some of the pens are near seals, and if the seals are nearby, the fish, apparently the farmers have said that the fish behave differently when they are nearby the water, and I think it's because of the sound transmission. And so if that's stressing out the fish, we want the fish to be well, so if there's something we could do to counteract that sound or understand where the predators are, that could be really interesting. And I've heard of some research about the sounds that fish make when they're digesting and eating, and maybe we could use sound, especially on days where there's super low visibility, to monitor the fish. Yeah, I don't know. I think there's probably a lot more work that could be done there. Yeah.
Okay. Thank you very much.
Thank you.
Again.
Thank you.
Thank you for the wonderful talk.